Today, our discussion is on the engineered thermal stability. Ever feel like you are fighting the weather just as much as the furnace? Here is the thing, we have spent decades optimizing the lower furnace, but we are still letting wet, frozen burden at the top, which is still our efficiency. It creates a lot of problems. So you are looking at dark geometric mess on the screen that represent the complex invisible thermodynamic trap we are about to solve. We are moving from dealing with the weather to engineering our way out of it. But first, let's look at just how big this problem actually is globally. So our second slide which represent the issues. The global exposure. Have you noticed how your operation changes the second the season shift? On this map, you see call out across every continent. From the North America, where boat deliver frozen material to India, where monsoon saturate stockyard for 3 months straight, even in mild Europe, coke hits 8% moisture and pellet hit 5%. So, what exactly is the result of this? That moisture is not just water, it's a massive energy tax that forces you to burn money before you even start making iron. And if you are running a high performance furnace, the tax is even higher. So, there is a high risk profile. Look at this gauge. It's pinned in the maximum danger zone. If you are pushing high productivity with natural gas or PCI, you are already operating on a knife edge. For every 100 kilo of natural gas you inject, you are adding 81 kilos of process moisture through the hydrogen reduction, which results in a massive declination of efficiency. Your furnace is already wet from the chemistry alone. Adding rain soaked coke on the top, that is like trying to light a fire with wet matches while someone pours a bucket of water on your head. When that happens, the physical space inside your furnace actually starts shrink. The process height, cross section. What happens when that top temperature drops too low? On the left of the screen, you see a healthy summer furnace with a full orange glow. On the right, the winter version has blue water droplets condensing early. These create a sludge layer that physically shrink your active process height. The space where the real chemical magic happens. So, result of all this leads to a decrement in the process efficiency. So you have effectively turned a world-class blast furnace into a smaller, cheaper one just because the top is too cold to keep water in a gas state. Naturally, as operator we try to fight back, but that often leads to a compromise cascade. And our next slide which is going to talk about this compromise cascade. Here is the thing, every fix has a price. Follow these four boxes with me. Cook moisture spikes. So you reduce oxygen enrichment to keep the top warm. Then you have to add more expensive coke which increase pressure drop. So you finally have to slow down the blast volume just to keep things stable, which result in a massive effect. By the time you have balanced the furnace, you have lost 7%, 7% of your production and increase your coke rate by 6%. So you have not solved the problem, you have just managed the decline. And if the moisture gets any higher, you hit the efficiency cliff. Now the efficiency cliff. This graph is one that keeps managers awake at night. You see two lines. The orange one stays flat until about 10% moisture. Then it shoots straight up like a rocket. At the same time, the blue production line falls off a cliff. What it means? Parameter adjustments have a limit. Beyond that 10% threshold, the process simply breaks down and no amount of tweaking will save your shift. So this is why we need to move from a reactive strategy to an engineering one. So our next slide is going to talk about the approach comparison matrix. So we have got three choices on this table. You can try logistic, but that causes material degradation. You can stay reactive with the furnace parameters, which we have seen is expensive, or you go proactive with the company's preheating module, which is discussed here. So what is the result? We de-ice and dry the burden directly in the existing silos. So no extra handling, no extra breakage. We fix the moisture before it ever touches the furnace. So let's look under the hood at how that actually works. So now coming to the system architecture. So imagine this 3D wireframe is your stockhouse. You see orange arrows representing dry hot gas pumped into silos and the blue arrows pulling out the cool saturated air. We are using a hot gas generator or even waste heat recovery to turn those silos into giant dryers, which has a tremendous result. We are using low grade heat to solve a high grade thermodynamic problem, keeping the material ready for the furnace 24/7. Now you might be thinking, wait, my silos are not designed to be pressurized. Now coming to the core innovation, pressure balancing. So you are right, standard silos are not pressure vessels. That's why the magic here is the pressure balancing. Look at the gauges on the diagram. It shows micro tolerance. The system operates on delicate balance of slight over and under pressure zones, which has a tremendous resultant. This engineering allows us to dry coke and pallet without needing any structural reinforcement of your existing silos. So it's a high-tech solution that fits into your current footprint. But does the math actually work out for the bean counters? So our next slide, which is about economic calibration. So short answer, we can say yes. Look at the moisture slider on the screen. While 0% moisture is possible, we find that drying to 1 to 2% is the sweet spot for economic stability. So what is the result? This creates a payback period of roughly 12 months. Think about that. In just 1 year of avoiding those winter penalties we discussed earlier, the system has already paid for itself. So let's wrap up with the bottom line impact. So let us discuss in our final slide about the final impact. So here is the big win. We take frozen pellet at 6% moisture and turn them into conditioned burden at 35 degrees centigrade and 3% moisture. And the effective result is a potential 20% increase in production and a 12% reduction in the coke rate. So this is a very uh, impactful result. So you are not just surviving the winter anymore. You are dominating it. We are transforming weather-induced vulnerability into guaranteed operation control.